Alright, so continuing on from where we left off, going to do some more Leetcode. I believe we left off on two sums, so that leaves us with this right here, top K frequent elements. Oh wait, no, group anagrams first. So again, these are the ones I already did. It has been some time though, so I'm going to be redoing them, hopefully analyzing patterns, utilizing good C++, modern C++ semantics, and just trying to get comfortable with some Leetcode. So let's do this. Yeah, alright, so group anagrams. Let's read it. Let's set it up first, actually. Blind 75. Group anagrams and main.cpp. Main.cpp and notes.md. I'm going to take from here, go to here. And take this right here. And I'm going to do import the vector. Alright, nice. Let's just throw this so my linter doesn't give me an error. Function not implemented yet. Alright. Alright. Alright, so the problem reads as, given an array of strings strs, group all anagrams together into sublists. You may return the output in any order. An anagram is a string that contains the exact same characters as another string, but okay, so it seems like a continuation. I'm gonna actually do this in Leetcode because I know that Leetcode kind of doesn't provide all the constraints. So anagram. Alright, so given an array of strings, get the anagrams together, you can return the answer in any order. Constraint strings.length consists of lowercase English letters. So this very much looks like a continuation off of valid anagram, which we did last time. The way we did this was that we had a frequency array, we kept that at a fixed size of 26 because we're able to do that of these two constraints. So given that, basically we would loop through S and T simultaneously, and for each character of S we would index it based on that character and increment it, and then for each character of T we would index that character and decrement it. And the idea there was that we would create some sort of offset. So if a character of S was incremented, then at some point later on, when traversing through the characters, a character in T should then decrement it, effectively putting it back at 0. And so if this was a valid anagram, then all of these would be put to 0. For this approach though, I don't believe I will be using the same method. So we can kind of just decompose this question down into a smaller bit. First of all, trying to solve how to determine if two strings are anagrams, and the way we solve that is by the is anagram. So let's do it this way. What would a brute force solution be? Well, a brute force solution would look something like calculate the frequency of this and then compare it to all the frequencies of here and then add it to some sort of bucket of a 2D vector, right? Calculate the frequency and then look at the rest, add it to some sort of bucket, and so on, right? So that would be the brute force. In this case, so I guess the tricky part here is we're trying to group all the common anagrams together, right? And if we were to do it the brute force way that I had mentioned, that there would be some problems, right? Because let's say I take this and let's say I paste it here, right? What if this array had, instead of this, let's say it had TCA, cat, and so on. If we were to take a look at this character, find the frequency, and get all the relevant frequencies into here, into one bucket, then that will look something like this, right? Act TCA cat. The problem with this is that if we continue on, get the frequency of this, and then look at the rest of the array, this will then create another bucket like this. Right, so this is not what we want, because here you can see that there's two buckets, right? But these two letters or these two words have already been captured in this bucket, so this won't work as a brute force solution. What's another naive approach? Well, we can just sort all the strings into here, right? We can have a separate array that will store all the strings into here. Sort all the sorted strings, right? So let's say, again, this was our input. How do I not include? No, that didn't work. Alright, that's whatever. So say if I were to sort these strings, right? This will become sorted, so what would it be? ACT, right? This would become sorted. This would be whatever it is, right? Let's just say it was tops. This will become sorted. This will be tops, right? This will become sorted. This will be ACT. The idea is that I have a separate vector of the sorted versions, right? And then essentially what I would do is loop through the sorted string vector, right? And then group alike, or group, I guess, group equal strings together, store them into a bucket / 2D array, right? Something like that. Yeah, so this could actually work. I'm not gonna code this part, or I'm not gonna code the brute force solution out, but that was more or less my idea of what would a brute force solution look like. So now the better approach, I believe, would be to do something similar like how we did last time, right? But instead we're actually going to be using a frequency map. So again, let's say I had, let's draw this out. So let's say I had ACT as one string, TCA as another, right? TOP STOP, right? And let's say I had cat. So obviously these ones should be grouped together, and then these ones should also be grouped together. So the idea here is to basically calculate a hash map for each one of these, right? Now that's a little iffy, right? Because that's creating what? N hash maps, which sounds a little skeptical, right? But say theoretically we were to create a hash map, right, of frequencies, or even just create an array. Oh, no, that's not what I want. All right, create a frequency array for each one of these, right? So let's say A, right? A had a frequency at 1, right? B is nothing, so that's a 0, C, and then so on all the way up to Z. Of course, we're accounting for T, right? So say we created that frequency array for each one. then we could essentially use that as our key value pair in our hash map, right? Where the key is going to be that frequency array, and that value is going to be a vector of the strings that share the same frequency array, right? So if this guy's frequency array matches up with this guy's frequency array, then they would map onto the same key, and then we would append these strings onto our vector as a value, right? One thing with C++ though is that we can't necessarily store an array, a vector, so on as a key, I believe. Let me double check that. So can we use a vector array? Oh, you can as a key in a, but not by default, unlike which only requires a comparison. Okay, so not by default, right? We need a custom hasher. What we can do though is just do exactly as that said, right? Create a custom hasher, right? So if we had a frequency array, right, that looks something like this: 1 right there, 0 right there for no B's, 1A, maybe 1C, and 1D, and so on. All we really have to do is just append these together and make them form a string of some sort, right? So this would be 1 0 1 1 and so on, and this would be fine, right? Because they would create some sort of hash, right, for this array. It's basically representing this array in a string representation so that we can use it as our key. So now our key is no longer a frequency array, but it's a string that represents the frequency array. And the vector will be an array that contains the strings that share that same frequency. So that's my idea behind it. Yeah. So let's say frequency map, right? Here's probably what we would do, right, in C++. So the pseudocode will look something like this, right? We would initialize our map, right, or initialize our frequency array, right, for each string in our input. What is it? It's called strings. So for each of our strings and strings, right, we'd essentially say something like probably say something along the lines of calculate the frequency, right? And maybe this would be initialized every time, right? And then calculate the frequency, right? Then convert the frequency into a hashable value, and then store into a hash map, right? That could look something like key.pushback string, and that's pretty much it, right? And then at the end we would, let's just say for each key value pair in that map, we would basically do result.pushback val, and so on. So that should be it. It's pretty much the idea there. So let's see if I can code this out. Alright. Let me set up. Let's grab the size, right? Let's call it an estimated size. Let's do cons auto ampersand strings. So reason for the ampersand here is because it's a string, and I believe it's less overhead to copy it as a value or copy as a reference rather than a value. What's the idea here? So find the frequency array. STD array, or array, right? It's of type that, has a fixed size 26, right? Frequency array. Let's do that. So it default initializes to 0. I believe that's using the default constructor. Or even more so, I believe we can do something like this. Alright. Then we would const char, or not const, but I guess it's char c of the string, right? We would say we would access the frequency based on the index of the character, and then increment it, right? Then convert to a hashable value. So then we're going to have, what would that be? For each num in frequency array, right? Let's say we have std string key is equal to nothing at this point. Key plus equals num, right? That should be fine. Let's do std2 string. Let's do that, and then insert into our hash map. Std unordered map of int std vector std string right. One thing though, this should be also a string. Maps a frequency array represented as a string to a vector of strings that contain the same frequency array. Alright. Lastly, so at what is it? M at key is pushback. Not pushback the string, I believe, right? And then after that, construct our 2D answer vector. So vector string ends, right? What could it be? So const auto ampersand use structured binding where key val of m and stop pushback or val. This looks about right. Alright, so let's go through it. We get the size of the string, our input string. We create our unordered map, right? So it's the string to a vector of strings, the string being the frequency array represented as a string. And we're going to loop through our string vector. So for each string, create the frequency array. Now for each character in the string, update that frequency array. Then create the hashable value, which is just a string, key plus equals std2 string, turn it to a string, Okay, this is very, very interesting. STD array and 26 frequency array initializes it all to 0 for each character in the string, right? Frequency C minus A plus plus, right? So increment that spot. Then convert to a hashable value, right? For STD string and frequency array key plus equals to STD 2 string num. No, I don't see it right off the bat. Okay, let's actually print out the key. Key. Let me just do this. I'm stupid. Interesting. They do map. Okay, how are they mapping to the same one? Sorry, no, I did not mean to submit. String would be what? String. What am I missing here? Why is the only one? Okay, now I am extremely confused. Oh my gosh. Okay. It's the way I'm constructing the keys. That's an edge case I have to be wary of in the future. So, this was on me. I have to be more thorough with my edge cases. So there is a specific edge case that I missed when I was creating my hashable key. So let's say in one instance, right, my frequency array looks like this, right? Of course, if I were to append it, right, it would look something like this. But who's to tell me that this 0 doesn't mean that the next character has a frequency of 0, right? Because this could be represented or viewed in different places, or in different, or this could be interpreted with two different meanings, right? In one meaning, A has a frequency of 1, B has a frequency of 11, C has a frequency of 10. If we were to combine them, then A has a frequency of 1, B has a frequency of 1, C has a frequency of 1, D has a frequency of 1. So we need a special way to we need a special way of basically representing this case where we have a 10, or just representing the zeros in our array. So instead of just doing a straight 0, then we could just do something like this, where if num is equal to 0, then key plus equals let's just say like a pound sign. That's probably safe, right? And then else. And hopefully this should work. Let's run it with this test case. Okay. Hopefully we get it. No, we don't. What? If num is equal to 0, key plus equals. Okay. We have 1, and then we have 1, 2, 3, 4, 5. Oh my gosh, no. A more robust way is to have a pound sign after every number we convert, right? So actually it's gonna be something like this. Okay, right? So before I suggest just to convert all these zeros into pound signs, right? But I believe a more robust way, or an edge case that we're missing, is something like this now, right? So who's to tell us that when we combine it, right, that this means that A has a frequency of 1, B has a frequency of 1, C has a frequency of 0. No, it's A has a frequency of 1 and B has a frequency of 10. These two are independent, so between each number we would just include a pound sign. And then over here, let's convert this to that, right? Over this. Run it. Passes. Run it, please. Okay. Ooh, okay. How is this faster? Let's note the things that they're doing to make this faster, right? They're using a dot reserve. Again, we mentioned that earlier. When you're using an unordered map, you should be using dot reserve because it eliminates the need of doing a increase in size, which would basically take all the elements in an unordered map and then rehash it. It's a lot of overhead, so we can just reserve that space ahead of time. So let's actually do that. So we know at most the amount of strings, or the amount of spaces we would have, is the size of the string. And the reason for that is because worst case scenario, all strings have different frequency arrays, thus resulting in each string having to have their own frequency array representation. So this will be m.reserve and so on. Okay, that's another optimization we can make. Oh, interesting. They're saying sort is highly optimized for short strings. So they were actually using my idea, the brute force solution, where we would just sort every string. Oh, very interesting. To me, this didn't really stand out because sort is just n log n, right? But they're saying it's highly optimized for short strings. Let's see how that works. Why is STE highly optimized for short strings or short vectors in C++? I see. Entire array fits into L1 cache, no cache misses, tight loop, super fast. Makes sense. Makes sense. Groups key.pushback. Oh, so he's not even having to create a hashable function, right? We just sort it, right? And then that sort would be the key. And then we push it back. Okay, that makes sense. Okay, so a couple things to note here. I'm gonna go like this. I'm gonna say optimized. Standard approach. Okay. So there's a couple ways we can make this better, right? We can just sort the string itself. Dot begin, right? And str.end. Sort is highly optimized for short strings. The reason for that is because using insertion sort for small input, fast, considering that a whole array could fit in a L1 cache. And what this means for us is that that means we have a lot of cache hits, no cache misses. Okay, nice. So that's why SCD sort could be highly optimized for short strings, right? Again, don't know why it's saying that. We already have. Oh no, it's algorithm. All right. Then all we have to do is that since we already sorted, that's in the hashable state. It's already in a hashable state. So we would say str, right? And then dot pushback. Ooh. Let's keep a copy, right? Copy. So, makes sense. They're actually saying here to do it the other way around. Sort the copy. Don't touch the original one, which is generally good practice. We don't want to mutate the input that we're given. Here, and then, okay, nice. So, sort eliminates the need to create a hashable for loop. Eliminates. Okay. Now here is something where pretty interesting, right? So again, they're having a result vector. They're also reserving the size. Let's reserve the size so we can avoid any deep copies, right? So ans.reserve, right? What's the most we can reserve in this case would probably just be n, right? Because there's n total strings. Okay. Now in this case, we can loop through our array, and what they're saying actually is to do a pushback std move. So in C++, one was std move, one was std move introduced. C++ 11. So we did not learn this in class, but I believe in C++ we have two types, an L value and an R value. An L value is something that doesn't have an identity. So no identity here. An R value is something that has an identity, right? So an L value examples could be 5, or in this case, int x is equal to 5. 5 is an L value. Or, sorry. I mixed it up. R value. 5 is an R value because it has no identity. So yeah, this is actually wrong. So L values actually have an identity. R values don't have an identity, right? So the R value in this case would be an x. This has an identity because it has a variable. It's stored somewhere. 5 gets lost after this line has been executed, right? Same thing in this case right here. X is equal to y plus 1. Y plus 1 will be an L value. Sorry, an R value, and x will be an L value, right? And this is important because for std move operations, right, he's basically invoking this move. I wouldn't say constructor, but I'm assuming the pushback has a where is it? Touch pushback. This is a value type, right? So this is what they are using, right? They're actually using this one right here that uses an in place back, and this one right here accepts an R value, right? And just to make sure I have that down, let's check. Let's see, plus an R value is one that doesn't have an identity, while L value is something that does, right? Oh wait, no. So persistent object. Okay, yeah. So an L value is something that has a persistent object. In this case, it would be x, right? So x is an L value. P also has an L value, right? It's basically the left side of the operator, or equal sign. So basically like a variable, right? Everything on the right-hand side is going to be an R value. This is an R value, right? Because you cannot take its address and so on. Okay. Now, can you explain why .pushback std move is more efficient, or should we be using .placeback instead? And walk me through the difference. Explain the efficiency and trade-offs. Okay, yes, std move object, right? Std move s, they're moving a string into a pushback. S is an L value, it has an identity, it has an address, right? It's a persistent object. Std move s casts it to an R value. Pushback sees an R value, calls the move constructor. Instead of copying hello, it steals the internal memory. Is an L value copy constructor, right? Allocates new memory, copies characters. O of n. Oh, okay. So I believe what that is saying is this right here. C++ place back or pushback with std move object. What happens here is that, let's say in C++, right, we have this vector that has this pushback function, right, pushback, and it's expecting an object where, let's see how they do it. Alright, so they're expecting an object, right, cons ampersand, let's just say some object, obj, right. when an object is passed to this parameter, it's going to create a copy of that. And for instance, if the object was a string, right, in order to create that copy, it's going to, so if object was a string, it will loop through each character in that string and copy it over to obj, right? But with a move or an std move where we invoke the move constructor, right, now we're expecting something, I believe that looks like this. Push back. Let me see if that's right. Value type obj. Oh, okay. Actually, I had that wrong. This will invoke the move constructor of obj, right? And what that does now is instead of looping through each character, all that simply is going to do is saying, hey, obj.data is going to be equal to, let's say, other.data, right? And then other.data is going to be equal to no pointer, right? So you're effectively stealing their data instead of having to copy it over, right? What that would look like in here is that, let's say in the copy constructor part, right, we have obj's copy constructor, right? And then we're essentially trying to do this right here. So object ampersand and then let's say other, right? Basically what we're doing is that, let's say these two were strings, right? Obj has its array to store the string of, or to store the characters, other has its array to store the string of characters. We're going to be effectively looping through each and single one of these characters and other and placing them respectively in their correct index here. This will be an O of n operation, right? But with a move constructor, this eliminates that by doing something called stealing each other's data, right? So this is invoked by saying, let's say you had your move constructor object ampersand obj, right, is equal to some r value, let's say std move, right, and then other. What this does now is instead, again, they both have their own respective arrays, right? But instead, what's going to happen is that, actually in this case, right, obj doesn't have an array. What's going to happen is that it's going to create that pointer, right, let's say pointer, and it's going to steal this guy's array, right, effectively saying pointer is equal to other dot data or something like that, whatever it is. And then what that's going to do is that now this pointer is pointing to this guy's data, right, was also pointing to this, but now we're going to say other, something like other dot pointer is equal to null pointer, right? We're effectively stealing the other guys' data and resources instead of having to go through that overhead of doing a deep copy for each and every single character and so on, right? Let's see if I have this right. Does this effectively sum up what the move constructor does, which is just steal the other person's data instead of doing a full deep copy? Before that was the same with and place back. Construct the object directly inside the vector. You already have an object that either copies it. You pass constructor arguments that builds the object in place. Okay. B now owns. A is still valid but no longer owns data. Okay. So makes sense. That was nice to know. So in this case, I'm assuming we can just say something like this, and then we can return the answer. So let's see if this helps me get a higher score. So before it was 66. Now this would be what? Optimized. Submitted. See, 15 milliseconds. Okay, so that was like a what, like a 40-ish millisecond jump. That's pretty good. All right, so let's move on. Actually, before I do this, let's do some key takeaways. Key takeaways. Use move constructor when we have an object already created. To avoid O of and deep copy. Right, what's another one? Sort is highly efficient for short strings because of cache utilization. Uses insertion sort. Or specifically, this you would use spatial locality. Alright, those are the key takeaways I took from this problem. Now let's commit it. Group anagrams. So that's good so far. Use restroom. Alright, let's continue. What's next? Hopefully I can redeem myself. Top K frequent elements. Ah, shit. Alright. Top K frequent elements. Top K frequent elements. CDP. Let's have a nodes.md. I'm gonna remove that. Don't really need it, and I'm gonna remove that as well. Yeah. All right. So this would be top K frequent elements. Right there. std vector, and let's just return constant or size t and size. Alright. So what we want is, given an integer array nums and an integer k, return the k most frequent elements within the array. The test cases are generated such that the answer is always unique. You may return the output in any order. So, what we want to do is return the k most frequent elements. Here we're returning 2 and 3 because what's the most frequent element? 3. It has a frequency value of 3. What about 2? It has a frequency value of 2, and so on. 7, it's the only one in the array. Of course, it's going to have the highest frequency, which is 1. K is always going to be less than or equal to the number of distinct elements in nums, and so on. Alright, so how can we do this, right? And I'm actually go here, remove that, discard changes, discard, discard, discard. Alright. So let's say we had 1, 2, 2, and 3. Move this over. So let's say we had 1, 2, 2, 3, 3, and 3. K is equal to 2. So what we could do, right, is let's say okay, say first approach is that we can sort it, right? And I believe that the input that we're given doesn't come sorted, right? There's no constraint telling us that it comes sorted. Leetcode might have more input output top k frequent elements. Okay. No, yeah, it doesn't always come sorted. So say we do sort it, right? That means all the numbers who are next to each other have, or all the numbers are going to be grouped next to each other, right? And in that way we can count the frequency, right? Let's say in this case we have more ones. In this case we would count, okay, 1 has a frequency, right? So maybe we can store a hash map of some type, right? Say we store a hash map of, where'd my pen go? Okay, say we store a hash map, right, where the key is the number, right, and the value is the frequency, right? So 1, we're going to increment the value, right, and then increment its frequency. We see it again, increment, right, so this turns to 2, see it again, increment, turns to 3, and so on, right? Then we would be doing it for all the ones over here, right? So we're effectively counting the frequencies of each one. And actually, because we're using a hash map, we don't really need to sort it anyways. We're going to come up with the same frequency hash map. So 3, 3, and so on. Now what we want to do is find the k most frequent okay, what we want to do is find the k most frequent elements, right? And so how can we do that if we have a hash map of values, right? And our values is the one that's telling us, hey, this is the most frequent element because it has a 3, and 3 is as high as it goes compared, and the only thing that opposes it is this 3, right? So we would return both 1 and 3. But the issue here is that how can we tell that this is the highest frequency? Well, first thing that comes to mind, right, if we had an array and we had an array of pairs where the key and then the value, right, so 1, 3, 2, 2, and 3, 3, we could effectively sort this array, right, and we could sort it based on the second value. And the way we can do that in C++ is through a lambda function, right? So if we had our sort, this is the beginning vector, the ending vector, and then our lambda function, right, which will take in a pair. We can just compare the seconds next to each other, or the dot second, which is this part right here, and sort it based on like which one has a higher value. And so if we were to sort it based on the higher values, now our array would look something like this, right? So 1 3 3 or 1 3 3 3 and 2 2. I'm gonna go ahead and say that that is the naive solution. So let's just note that down, right? So brute force, what we can do is say create a frequency map and vector increment the frequency, right? And then for each key value pair in map, we would let's say we had our vector v, right? We would say vector dot push back, create a pair, right? So key value, right? And then sort based on the pair's second value in descending order. Return the first k elements in that sorted vector of pairs. Alright. But what's the runtime associated with this, right? The runtime is runtime would be O of n, and space complexity would be O of n as well, right? Because we're creating or to be more specific, I guess, O of 2n, right? Because we have O of n for this vector and then O of n for this frequency map, but this really just decomposes down to O of n. Now, is that the best solution though? I don't think so. Is there an O of n solution, right? So going back to this, right? Let's say I had 2 2 2 and 3 3 3. Okay. How can we go about this? Okay. I don't think there's any workaround about finding the frequency map, right? So I'm assuming, let's say we construct that frequency map, right? We construct that frequency map no matter what. So our key is the actual element, our value is the actual frequency. So say we had 1 here, value is 2. Say we had 2 here, value is 3. Then say we had 3 here, value is 3 as well, right? I guess the only bottleneck that I'm running into is trying to find which one has the highest frequency. Okay. Well, okay, sure. Let's okay, I believe we can, it's safe to say that the value of each one of these will always be less than the size of the vector, right? Because, yeah, that would be the case, right? Because if one of them was greater than n, then that would mean that it would basically overfill the array. So we know that the frequency value is confined within the size of the input vector. So what we can do is that, let's say we initialized another vector, right, of size n, right? So in this case, let's condense this down, right? Let's just say this was Let's take those out, right? And actually, let me just erase this. Can I erase it? No, it's not behaving. All right. Let me go back to my pen. If it'll let me. All right. Let me just. Okay. So say we had 1, 2, 2, 3, 3, 3, right? Say we had that, right? And we created a vector of the same size, so size is 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Our hash map would contain 1 maps to 1, right? 2 maps to 2, and 3 maps to 3, right? Then we can basically iterate through all of these, right? And say, okay, based on the value, so based on the frequency, index our array that we have made, right? So this will be at index 3. And for each one of these, we're also going to store another vector that will hold the key of that, right? And the reason why we made it a vector is because there could be more input that has the same frequency, right? So now 4, 3, right? And so we would store 4 here as well, right? If we were to continue this on, we would store 2 inside this vector, right? And store 1 inside this vector as well, right? Okay, that looks good, right? And so if we wanted to return the k most frequent elements, again, this whole vector is holding all of our, we're basically treating this vector as some sort of map where the value or the frequency is our key, right? And so all we have to do is traverse this vector backwards, right? Because the highest frequency will be stored at here, at this index, right? The highest next frequency will be at this index, and so on, right? And so we would traverse this backwards, we would hit here, and then just return the top k most elements in this vector. If 4 didn't exist here, we would append 3 to our answer vector, and then keep going until our answer vector has a size of k. So that looks good to me, right? So let's code this out. Let's say 2D bucket, right? Oh, here's what we want to know. We can create a vector. Okay, first create a hash map. Let's say frequency hash map that maps a key to its frequency, or let's say more so a number to its frequency, right? And for each frequency value, actually, let's go back and say this. Create a vector of size n, right? And then we would store the frequency, or append the key. Oh, wait, actually, okay. For each key value pair in the map, we would store, or holy shit, index the vector based on the frequency, and then append the key to that vector. Append the key to, let's say, vector at frequency. Okay. That's pretty much it. And what this does now is that, oh, okay. By the way, this runtime is not n, it's n log n. Okay. And now we can say that the runtime is at a comfortable O of n, right? because just O of n to create the high frequency hash map, you're just looping through the vector once, and then you're looping through the hash map again, O of n. Yeah, so technically O of 2n, but it condenses down to O of n. Alright, so let's code this. Let's create our frequency hash map. STD on map, right, and right, and for each and num and nums. We can actually go like this too. Num plus plus, right, and then what could we say? STD vector, right? STD vector of integers, right? This is our bucket, right? And then we're going to have our STD vector integer ands. So this is the bucket that we're going to be storing the keys into based on their index, which was their index is going to be given based on their frequency, right? So one more time, right? If the value is this is essentially what our bucket would be, right? And so if the value was 3, right, 0, 1, 2, 3 would be stored into here, and so on, right? Let's say though we had 3, 3, 3 instead of all of these, right? Then the frequency would be 6, 0, 1, 2, 3, 4, 5, 6. So the size would actually have to be n plus 1 here. Ooh. Okay. Vector of n plus 1. Right. And answer, we don't know what that could be, right? But we can reserve it, reserve the size, and say it's going to be at most n. Or it's going to be k. Okay, nice. Now store our key value pairs into the bucket. Where the value such that, or an example is m at value is equal to m at value dot push back key, right? Actually, that wasn't really helpful. Okay, index our bucket based the value slash frequency. Okay, that's more accurate. So for const auto, am I using key here? Yeah, val, right, in our map. M at val dot push back key This is very interesting. Key. Remember reference base type, map type, aka int is not a structure or union, right? Oh, okay. This actually makes sense. We're using bucket. Yeah. Okay. Right. So construct our answer vector. Okay. Now for int I is equal to, we want to start at the end right, towards n, so n minus 1, right? And we could say while I is greater than 0, we don't necessarily have to include 0 because there won't ever be a case where something is going to be stored here, so this is effectively not useful, right? Because what does that mean? There's no instance where a value can be mapped to a frequency of 0 if that value exists in our hash or inside our input array, right? So we could say something like this, minus minus I, and then we could say ans dot pushback no, and then we have to, so we're traversing backwards, so traverse here, traverse here, traverse here, traverse here, but we also have to traverse each one of these as well. So for int num in ans at I, right, if ans dot size is equal to k, then we would just return ans. Else ans dot pushback num, right? Tell me that's right. Yeah. Alright, and then we would just return ans. This is bucket. Alright, hopefully this is it. Okay, let me redeem myself. Let me do one quick check and see if we can do a one shot at this. So we get the size of the number, right? We create our frequency map, and then we create our bucket, right? And then for each of the values in our frequency map, we're going to map it onto our bucket and then push the key associated to that, right? Then we're going to have our answer vector reserve at most k elements because we want to return a vector of the, we want to return the k most frequent elements. And then we're going to traverse it backwards because backwards is going to contain the highest frequency. And then for each of the numbers that we traverse through, we're going to check, hey, is our answer size already meet the top k that we're interested in? If not, then we're going to push it back to our answer vector and then continue on. So I believe this should hopefully work. Let's do Leetcode first. I feel like Leetcode is more forgiving. Fuck. Okay. Alright. Why did this fail? Right. So 7 has a frequency of 2. It's going to be mapped onto 7, 7. We're only interested in k is equal to 1. My output gave a null. Interesting. So I think here we're actually interested not in n but bucket dot size. Right, bucket dot size. Wow, was that it? Okay, nice. Alright. So how does someone optimize their solution? They reserve the unordered map. Okay, sounds good. We can also do a reserve of the unordered map. I guess it will be n, right? Num's that size. Okay, yeah. I don't know why they didn't just use n. And max frequency 0. What's the topic under here? Way too bright. Okay. What is he doing here? What the hell? Alright, so for each of the numbers, count, okay, add it to the frequency map. Max frequency is going to be max frequency. Okay, so we're keeping track of the max frequency. Max frequency plus 1. So he's not, okay, because if the max frequency was, let's say in this case, let's say we had our 1, 2, 2, 3, 3, 3, 3. What I was doing here was I was allocating a size of n plus 1, so this would be 1, 2, 3, 4, 5. So my size would be a 6. But he's doing the size of the max frequency because that makes sense, right? We only need to keep track of the max frequency that ever appears in this vector. So the max frequency in this case would be caused by these 3, right? So max frequency, and he does a plus 1. Max frequency plus 1, I guess that makes sense, right? Because if max frequency plus 1 will give us a size of 4, which will allow us to index at index 3. So yeah, it's actually really smart. So yeah, we can do that here by simply saying keep track of max frequency to prevent over allocating unnecessary space in our bucket vector. Right, so max frequency is equal to 0, right? And then max frequency is just going to be equal to the max of max frequency. Max frequency, right? Between that and then here it's just max frequency plus 1. Okay, that makes sense. Vector int result.reserve k. Nice, that's what I did. Pushback return result. Yeah, alright, pretty much what I did. This one took a while. Let's save this. Most frequent element. Alright, what am I at? An hour 30. Okay, let's finish off strong. Let's do one more. Okay, encode and decode a string. Alright, so design an algorithm to encode a list of strings to a string. Okay, list of strings to a string. The encoded string is then sent over the NAT grid and is decoded back to the original list of strings. Okay, interesting. So how can we encode a string? Like through, what's it called? Caesar cipher. Contains any possible characters out of the 256 valid ASCII. Okay, so my idea, okay, let me at least set this up. Encode, decode, string. That's CVP, no it's not. Alright, okay, I guess if it contains all the possible ASCII characters in a string, that could be a problem, because my first instinct was, say that I had this list of strings, right? Let's say I had he, and then also I had low, right? My idea was just to simply combine them, right? Combine them with some sort of delimiter between them. And then if we wanted to decode it, we would just find that delimiter and then convert it back to the list it was. But the problem with that right off the bat is the same issue that we had when we were creating our hashable map. The idea is that, or the issue is that, what if the string was this, right? And then with something like this, right? If I were to combine them, now it looked like he pound that pound because I joined it, right? And then the pound again, and then look. So now the issue is what's gonna prevent me from parsing it like this, right? So what I'm thinking is that, can we add a delimiter? And if we can, how do we parse it correctly? Given that it can be any value out of the ASCII. Ooh, okay, we forgot this one. Okay, so that's an issue, right? What's a better way? We can possibly, right? The issue is this, right? What if we had a double hello, right? We want to convert this back into he and then low, right? But how can we do this? Maybe we can also add some additional information here, right? What if we said we also stored the length of what the next string should be, right? This length should be 3, right? So now I had he pound 3 pound hello, right? So now what this is going to tell me is that if I parse it forward, right, hey, we ran into a pound and we ran into a number. Now we know that this is some sort of delimiter, right? So then we can just say, okay, we're going to extract away the number, right? The number we found out was 3, so then we're going to parse the next 3, or I guess 4 in this case. We're going to parse the next 4 characters and store that into our list. But again, this could run into the same problem where, let's say the strings we're given now is he, right? He pound 3 low, right? If I were to combine this, okay, wait, no, I did that one wrong. What if it was 3 low? Right, in our array. Now if I were to combine it, it looks something like this, right? Pound, right, it looked 4, right, because there's 4 characters here, 3 low, right? Now what's to tell me that this doesn't represent 43 characters that we have to parse on the right hand side? So I guess I can just encapsulate this by this delimiter and add another. So this is saying, okay, start of the metadata, end of the metadata, parse out the metadata, and then parse the following string based on that metadata. Okay. So I think this is just touching upon how to reliably encode stuff, right? So let's say, caution, there's a couple of things we have to be worried about, right? We have to be worried about, can't just simply join strings a delimiter, right? i.e. we can just give this example, right? Let's say delimiter was a pound, right? Then this would be encoded into he pound hello. How to decode this, right? So store extra metadata about how many characters to parse, right? So instead of doing this, right, we could say delimiter plus length to parse, right? So now, and then plus delimiter. So now this will be parsed as 4 and 3, right? And so now the way we would parse that is just continue on, right? And this would also probably have something like pound to pound, right? Okay. So let's work on the encode function first. Right. Let's get the size, right? Size t. I realize that I haven't been using size t in here as well. That's fine. Okay. Size t and string that size. Right, and then we would essentially just loop through std string encoded string cons auto strings, right? And then what would we say? We would say something like get the length, right? So int length is equal to string.length. Right, and then we would say, okay, encode with delimiter pound plus length plus pound, right? So if that's the case, then encoded string is going to be plus equals, right, that delimiter, right? Let's say that delimiter plus std to string the length plus this, right? And then finally append the string as well, right? Okay, and then we would return encoded string. Okay, now we would get the size of this, right? So n is equal to x.length, right? And then okay, for each char c and s, right, would say if c is equal to that, right, okay, let's actually do it this way. So size t, I is equal to 0, right? I is less than n plus I. So if I does not equal to n minus 1, right? And check if the next character has a number. S at I. If S at I plus 1 okay, so what if though, wait, does it contain, yeah, it can contain numbers. Okay, what if we had this edge case though, where it was hello pound 3 as a string, right? But say it had something like that, right? If I were to join them together, it'd be hello pound 3, and then my delimiter, which is pound 1 2 3 4 5 5 pound 3 pound this, right? I would see this and I would be like, okay, parse the next 3, and so what is the right solution here? I'm kind of stumped. Alright, let's take a look at a hint. That's what I was trying to do. Okay, so it looks like he's basically doing what we're doing, right? Okay, let's continue on blindly, right? Maybe we don't need this, right? If we ran into, let's say, if SI is equal to pound if S at if I does not equal, to prevent overflow, right? And S at I plus 1 is there constraints. How to determine if a string is a number in C++. Is digit. right? Because it could be a 3-number digit, right? A 3-digit number, right? Because it could look something like 10, right? So and I is less than n, right? We would say length, right? And then length plus equals SI. Yeah. Convert a string to a digit in C++. STOI. Okay, that's what it was. And then right, so we have the length now, and length is actually going to be set to 0, right? So we have the length now. This is get length of a string to parse, right? And then what we would do is okay, and then index to parse. We would also say index to parse is going to be equal to index, right? Okay. Mind you, we have a which I'm not sure what to reserve the size for, but okay. And index is equal to 0, or index. So while s to parse, right? And index is equal to 0, right? Index is less than index to parse. We would say something like parse string plus equals SI, right? Or SI. What would it be? Okay, I think I'm going about this wrong. Oh wait, no. Okay. So we can use index to parse. Right? And then say less than length. Hopefully that makes sense. 2 parse. Right? And then plus. And then ants dot pushback parse string. And then I plus equals length. Return ends. Not 100% sure about this one, so let's just try it out. Where'd it go? Encode and decode a string. Oh god. What? How to use SWE story C++. The string header. Okay, I'm confused. What am I STOIing? It's an empty string. Okay. So I'm getting length of 5, right? And next 2 parse. I think actually I would have to do index is equal to 0, right? And then index of parse plus index, and then increment index. And then it's actually while index is less than length. Okay, a little better. I'm low-key tired, so let's see how he does it. Solution. To string size. For all the sizes and sizes, to string the size, right, plus a comma. Oh, so he's storing the sizes. And then he's also storing the string at the end and then decode it. Okay, wait, let's see how he's doing this.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem. And that works because we're only going to read one delimiter. We're gonna expect a single pound sign no matter what, right? So even if the first character here was a pound, it still works because we're going to read an integer 4, read a single pound sign, and then say, okay, take the next 4 characters, even if they include a 5 and a pound sign, because the next word is going to be 5 characters long. So this is kind of how we're storing the integers inside of the encoded string so that we know how to decode it.
Okay, but what if the first input was neat and 5? Right. I feel like there's so many edge cases here. Let's see. So looky, I had the right idea with pound length pound. I think it's just my stupid decoding that's off. Let's see if I can fix it. Shit. Alright. What was I getting on here? I was getting hello and then empty string and empty string. Why was I getting empty string and empty string? Okay. Given this, right? Let's say I had this. This would be 3, 5. Hello, and then 3, 5. World. Right. I is equal to 0, I is less than n, right? If, and I should parse. So say we're here, right? And then SI is equal to pound. Okay, SI is equal to pound, right? So is the next one a digit? Yes, it is. The next one is a digit. So we're going to try and compute the length, right? To compute the length, it's going to be index is equal to I plus 1. So it's starting at here, right? And while SI index does not equal to a pound and index is less than n, yes, length plus equals index and then plus the index, right? So now index is there. Okay, makes sense, right? And then the index to begin parsing at should be at index plus 1, which is going to be hello, right? And then the parse string is going to be index is less than length. Length is 5, so 0, 1, 2, 3, 4, right? So it's at 0. Nice. Then we got 1. It's at 1 is less than 5. Yes. 1 is less. 2 is less than 5. Yes. 3 is less than 5. Yes. 4 is less than 5. Yes. 5 is less than 5. No. Okay. Oh shit. Okay. Bad alloc, dude. Wait, I was never... Wait, why not set I to be where index was left off at? Right, so it's going to be index minus 1. Oh, okay. It's not index minus 1, but it's index plus index to parse minus 1. Oh my gosh. If it works, I'm done. I'm hella tired. Holy shit. Alright. Ooh, I don't care. Alright. Damn. Look, he wrote barely any notes. Okay, this was just some parsing. Key takeaways. When you're encoding stuff and you're running into edge cases like this, store extra information like the metadata, right? Metadata being the length of the string and so on. Yeah, I'm gonna cut it right there. It's pretty tiring.